Number of terms in a finite geometric series. Example 3. How many terms are in a geometric series? That is 3 plus 6 plus 12 plus dot 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 plus 768. So what we know here is we have a geometric finite geometric series, but the problem here is we don't know the sum and we don't know the number of the terms, so it's gonna make this problem with two unknown. But in order for us to solve this problem, we are going to solve the number of the terms in the geometric sequences, how many are, because the difference between a geometric sequences and finite geometric series is the operation are different, but the number of the terms might be the same. So in this case, for example, if we are looking at the definition of the explicit formula, we have a in a n is equal with the a1, the first term, time a common ratio in exponent n minus 1. So this is the geometric series. And now what we have to know here. Now we already know the finite term here. The finite term here is 768. So it's a 768 is equal with the first term is 3. We already see here the first term here is 3, this one here, and time a common ratio. Common ratio is if we are dividing the second term by the first, or every term by the previous term. 6 divided by 3 is 2. 12 divided by 6 is 2. So the common ratio r is equal with 2 in exponent n minus 1. So now here we divide everything by 3, this equation. We divide by 3 everything. And what do we get here? We divide by 6. You divide by 3, I'm sorry, 768 divided by 3 is 256. We can use you can verify with a calculator this result. So, and this is in exponent 2 in exponent n minus 1. And now we are using the definition of the logs, and we convert this into the log, and the base of the exponent become the base of the log, which is a log 2 here, is a 2, log 2, and 256 is equal with the n minus 1. N minus 1. And what do we have here? Now n minus 1 is equal, we are changing the base here, and this is going to be equal with this way. Is going to be log 256 divided by log 2 is by log 2, and we are adding everything plus 1, and n is equal with the log 256, the common log 256 divided by common log of 2, 256 by common log of 2. Plus 1. And we calculate everything here. When you calculate this common log of 256 divided by log 2 is going to give you 8, and the plus 1 here is going to be 9. So this finite geometric series is going to have 9 terms. So this is going to have 9 terms. And for example 4, we are going to the next slide. Example 4 is the sum of geometric series is 155. So the sum here, let me write sum Sn is equal with 155. And the first term of the series is a 5. So the first term, let me write A1 is equal with 5. And what says this? The common ratio R is equal with 2. And we already know the formula for the sum of finite series is Sn is equal with the first term A1 time 1 minus common ratio in exponent n divided by 1 minus common ratio. And now instead of Sn we are plugging here 155. We already have 155, and we can see, can we make this equation with one unknown? Because in the example 3 we couldn't do it. That's why we used this explicit definition of geometric sequences. And this one here, A1 is equal with 5. A1 is equal with 5, and here is 1 minus a common ratio is 2 in exponent n. We don't know what is n, so n is unknown, but here is 1 minus common ratio is 2. So as we see, this problem is easy to convert to make as equation with one unknown. Unknown is just n, so we can solve it. And now this 5, 1 minus 2 is minus 1, and 5 divided by minus 1, and every whole this numerator divided by minus 1 is going to be minus 5 here. Here is 155. 155 is equal with a minus 5. Minus 5 times 1 minus 2 in exponent n. Minus 2 in exponent n. And we divide the whole equation by minus 5. By minus 5, and we divide the whole equation by minus 5. 155 divided by minus 5 is minus 31. Minus 31 is equal with the 1 minus 2n. Minus 2n. We don't need this parenthesis, but okay. And now we are subtracting minus 1 both sides. When you subtract minus 31 minus 1 is minus 32. Minus 32 is equal with a minus 2 in exponent n. Then we multiply by minus 1 everything, because I don't need to be negative. And this is going to be 32 is equal with 2 in exponent n. 2 in exponent n. Now we are using the log definition, and when we use the log definition, we convert this into the logs, and the exponent become a base. The exponent here become the 2 becomes a base, and 32 is here. 32 is equal with the n. And now we are changing this, the bases we changing base of the logs, and n is going to be equal with the log, the common log of 32 divided by the common log of 2, the common log of 2. And when we divide everything and using a calculator, n is going to be equal with 5. So in example 4, in this case, this series with those given information has 5 terms.